Hello students, in this video we'll discuss matrix multiplication. Let's suppose, to start, that A is an m by n matrix, and B is a p by q matrix, okay? What does this mean? This means that A is a mapping that goes from what you can input n-dimensional vectors into A, and you will output an m-dimensional vector. And B, we can think of this as a transformation or a mapping of what? You can input q-dimensional vectors and output p-dimensional vectors, rq to rp. Okay? And what do we want from matrix multiplication? What we want, our defining property, we want A times B applied to a vector x to be equal to A applied to the vector bx. I want this composition rule to be true. So I'm going to define matrix multiplication in such a way that this rule is true. Now let's think for a moment what has to happen over here. In order for this to be true, we know that B is going to take something where? It's going to take something in RQ. So x has to be in where? X must be in RQ to satisfy the rule for B. And it's going to output something in RP. So this thing over here is going to be in RP. But A needs to input n-dimensional things, so this has to be the same thing as Rn, so P must be equal to n for this to make sense. So from now on, we're going to replace this P over here with an n. So B is really an n by q matrix over here, okay? And so now, in this case, what we have over here is that this is going to be an element of Rn. And I know how A operates on Rn, right? So now what we can do is I can define the matrix multiplication. Now we can define AB to be A, and I'm going to write B first. B has what? B has q columns, so I'm going to have a B1 is the first column, B2 is the second column, all the way down to BQ is the qth column over here. So that's what B looks like. I just write it in column form. And of course, all of these B1, B2, those are the what? Those are going to be the columns of those are things in Rn. So all of these columns over here are n-dimensional vectors. This is an Rn. This is an n-dimensional thing. This is an n-dimensional thing. Those are all n-dimensional things. I know that A can input n-dimensional things. So I can input n-dimensional things into A. So by definition, this is going to be, so there's a definition. This is going to be equal to A of B1. That's going to be the first column of my output matrix. All the way down to A of BQ. Like this. Now remember that these are m-dimensional things over here. This is an m-dimensional vector. That's m-dimensional now. M-dimensional, m-dimensional, m-dimensional. So I have m rows and q columns. So this is m rows and q columns. So A times B is going to be an m by q matrix. M by q matrix. Okay, excellent. Now let's carefully examine how we're going to find the elements of this matrix over here. So let's do an example first, just a real simple example. If, for example, we wanted to do 1, 2, negative 1, 1 times the vector times the matrix 3, 1, negative 1, 2, right? This is going to be what? This is going to be a matrix. I'm going to do a 1, 2, negative 1, 1. The first column, 3, negative 1. And then the next column is going to be a 1, negative 1, 2, 1. And the second column, 1, 2. Okay, great. And so now, of course, what is this going to be? This is going to be 3 times the first vector, negative 1, 1, minus 1 times the second column, 2, 1. And then over here, what we have, we're going to have a 1 times 1, negative 1, and then 2 times the second column, 2, 1. So if we simplify this, what are we going to get? We're going to have a 3 minus 2. 3 minus 2 is going to be a 1, okay? Then we have a negative 3 and a negative 1. So negative 3 and negative 1 is going to be a negative 4. Negative 4 down over here. Over here in the second column, we have a 1 plus a 2. That's going to be a 5. And then finally, we'll have a negative 1 plus 2. Negative 1 plus 2 is a 1. That's going to be the product of those two matrices. That's how it works in an example. But there's actually a more efficient way of doing this as opposed to just doing matrix, vector, matrix, vector, matrix, vector, and adding everything together. Let's carefully examine this thing over here, right? So what I'm going to do is I'm going to look at the jth column over here. The jth column is right over here. So the jth column, of AB is going to be A applied to BJ. A applied to the vector BJ. Now, what will that be? That's going to be A applied. I'm going to write it out as a full column. That's the jth column. So and remember, the B has these outputs over here. So we're going to have a B1J all the way down to BNJ, because it's an n-dimensional thing over there. So B1J through BNJ, okay? So what will this be? This is going to be B1J times A1, the first column of A, plus B2J A2, the second column of A, all the way down to BNJ AN, the nth column of J, okay? Now, if I want to find the ith entry, if I look at the ith row of this thing over here, what will that do? The ith row of this thing, so this is the jth column, and now I'm going to look at the ith row. The ith row of ABJ will be what? Well, it's going to be B1J, and then so this is the A1, for example, is what? So A1 is the column vector. It's going to be A11 all the way down through A. We're in the first, we have how many rows? We have M, right? So M1. So A is an m-dimensional thing, right? AM1, for example. So in the ith row is going to be what? It's going to be AI1, right? So I'm going to have an AI1, B1J. So what we have over here, so that's a B1J A1, right? So what we have over here, so we'll have an the ith row is going to be A, and of course, what will these things look like in general? So this is going to be an A, so for example, AN will also be what? Will be A1 row is 1, column is N, all the way down to AMN, right? So if I look at the row is going to correspond to this, this first entry over here, right? And so we're going to have a what? We're going to have a A1I, so the row is I1, plus B2J, a row is I2, all the way down to BNJ, AI, and then N. And so what we see over here is, I'm going to write this in sum notation, right? In sum notation, this is just the sum. K goes from 1 up to N of A, I, K. I'm summing over the second entry over here. And then B, K, J. So this over here is exactly the what? This formula over here is the I, J entry of A, B. And so what that is that's exactly just the dot product of the rows of A with the columns of B. So what this thing is over here is this is the dot product, the rows of A, row of A, dot product, columns of B, right? So we do row dot column. That's what we're going to do. So in further videos, we're going to see example of doing row dot column to find the IJ entry. So for example, let's do this with this example right over here. So what do we get? So let's think about it. We're going to have the 1, 1 entry is going to be the row dot the column. So I'm going to have a 1 times 3 plus 2 times negative 1. What would that give me? 1 times 3 is 3, plus 2 times negative 1, that gives me a 1. Good. Row 1, column 2 is going to be the 1, 2 entry over here. So row 1, column 2 is going to be what? A 1 plus 4, that gives me a 5. Great. And then what can we do? Then we could say second row, first column is going to be the 2, 1. That's going to be a negative 3 and a negative 1. That's a negative 4. That's exactly what we have over there. And then second row, second column is going to be a negative 1 plus 2. That gives me a 1. So our row.column approach is equivalent to this approach over here just by carefully looking at the indices. Of course, this formula may look complicated, but remember that A is the first matrix, so the I is fixed over here. That's the ith row. And then the column is the corresponds to the B matrix, that's the J, and then the J is in the column entry, and you're summing over the row, this K element, this first index over here is in the rows of B and then the columns of A, so you have row.column, 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 and so this is a very efficient way of actually computing matrix products. We'll see in future videos how using this definition, even though it looks complicated from the sum perspective, if we think of it as row.column, is a very, very easy way of computing matrix products. Thank you very much.